All right, this is Pre-Calculus A. We're in Unit 4, Polynomial and Rational Functions. We're in Lesson 4, Complex Zeros of a Polynomial Function. So we're on our quest again to solve or find zeros for polynomial functions. But the simple fact is, if you've ever solved quadratic equations, you know that not every polynomial function has zeros, and sometimes they have complex zeros. Okay, so we're gonna do an example of that. So here's the polynomial function I want to examine. So we've got f of x. F of x equals x to the fourth plus 2x cubed minus 17x squared minus 66x minus 120. Okay? And what I'm after is all the zeros, both complex and rational or real. Okay? And so using the rational roots theorem allows me to at least identify what the possible rational roots are. So we take factors of 120, which are 1, 2, 3, 4. Actually, I'm going to do it in pairs here so I can get them all here. So 1 times 120, 2 times 60, 3 times 40, 4 times 30, 5 times 14, 6 times 20. Actually, something is off there. 6 times 25 times 20, 24. 5 times 24, that's what was off. 6 times 20. 7 doesn't go. 8. 8 goes. 8 times... Okay. 8 times, what is it? 40. 8 times 15. Okay, 9 does not go. Yeah, because 9 doesn't go into 30. Right? 10 into 12. Okay, and I think we got them all. And plus or minus on every last one of these. All over factors of 1, which plus or minus 1. So all of my rational roots are going to be in these lists of numbers. Since I'm dividing by 1, there are no fractions here. So that's perfectly fine. Okay, and so you can use synthetic division, or you can use long division. I prefer synthetic division to test for roots, rational roots. Okay, I'm going to try using some of the smaller numbers. Now we might try 1. We're going to find that doesn't work. We might try 2. That doesn't work. We might try 3. I'm going to try 3 here, and let's see what happens here. So we're going to try using 3. Now, by the way, this is akin to dividing by x minus 3, right? When we use synthetic division. So we include all the coefficients, 1, 2, negative 17, negative 66, and negative 120. Do remember that if you have a missing power, that you need to include 0 as its coefficient. We need coefficient placeholders in those cases. Okay. And so let's see what happens here. Bring down, multiply, add, multiply, add, multiply, add, multiply, and we're going to get a very large negative number that's not going to end up in 0. So we know this one's not going to work. But don't forget, the positive root is different from the negative. So let's try negative. Okay, so negative root. Okay, so 1, negative 3, negative 1, negative is positive 3. Okay, negative 14, positive 30, 42. Okay, less 66 less 42 is 24, negative 24. 3 times 24 is 60, 70, 60. Yeah, that's not it either. Okay, and so that runs into, oh, because 3 is not a solution. Okay, so 3 doesn't work. All right, but let's try 4. All right, you can get a feel for this guess and check, right? Approach to it. You're going to be doing a lot of false paths, dead end paths. Okay, 4. Okay, 4 and 2 is 6. 6 times 4 is 24. And let's see, 3 is 7. Okay, 4 times 7 is 28. 60, 50, 40, 38. 4 times 38 is not 120. Okay, so let's try negative 4. 1, negative 4, 4 and negative 4 and 2 is negative 2. Okay, negative times negative is positive. Negative 9. 9 times 4 is 36. Negative times negative is positive 36. Negative 30, and there we have it. Negative 4 times negative 30 is positive 120, and we get a result of 0. All of that to get one division. All right. But what's really cool now is I can factor on this. I can factor on factors of 30 instead. Factors of 30 are 1 and 30, 2 and 15, 3 and 10, 4 doesn't go, 5 and 6. So our list of factors, plus or minus, is much smaller here. I'm going to try 5, and what's really cool here, I don't know if the lesson brought this out, but you can continue your division right here. So try putting 5 right here. Okay, and just continue your division right there. Just kind of a division ladder sort of scenario going on, ignoring the remainder. So bring down 5, 3, 15, 6, 30, 0. There we go. Okay, there we go. And so here's what we have determined. We have determined that x minus negative 4 is a factor. We have determined that x minus 5 is a factor. X minus 5 is a factor. And we've determined from here that 1x squared plus 3x plus 6 is a factor. Okay. Now we could continue to try, we can try rational roots, factors of 6, 1 and 6, 2 and 3, plus or minus. We've already tried both positive and negative 3. We haven't tried positive and negative 2, but we could, and we would find but they all fail. So we're out of rational roots. So we're going to apply the quadratic formula to this part here, right? Basically what we're doing is we're solving x squared plus 3x plus 6 equals 0. Okay? Remember the quadratic formula is negative b plus or minus square root b squared minus 4ac all over 2a. Okay? And let's work that out here a little bit. Okay? Negative 3 plus or minus 9, square root 9. 4 times 6 is 24. So right away we know we're in trouble because we're subtracting something big from something small. We're going to get a negative square root, and we can't square root the negative. That's where complex numbers come in. Okay? So this is the square root of negative, so I'm going to extend that out here, plus or minus the square root of negative 15. Negative 15, square root of negative 15. Okay? And basically what we do is we think of the square root of negative 15 as the square root of negative 1 times the square root of 15. And the square root of negative 1 is I. So there we go. So this is negative 3 plus or minus I root 15 over 2. Now that's not typically the way we express complex numbers. We express complex numbers this way. Negative 3 halves plus or minus root 15 over 2 I. Remember, in the form a plus bi. Now remember, this represents two solutions. And this is one of the big ideas of of this lesson. Complex roots always come in pairs. The complex number and its conjugate. So if I'm listing zeros, my zeros are -4, 5, 3/2 plus square root 15 over 2i, and 3/2 minus square root 15 over 2i. Okay? And this meets the requirement that a fourth order polynomial has, it looks like, 4 possible zeros. If you allow for complex zeros, it will always have 4. And if you allow for double roots being expressed or counted twice. All right, so that's the approach that we use for finding complex roots of a polynomial function.